It's a real pleasure to introduce Ryan Hickox. I've been trying to get him to come in for quite a while now, so I'm super excited that he's here, and I appreciate you guys all coming and listening to this talk. I've known of Ryan's work for quite a long time, and then I think I finally actually met you in person at this crazy conference in Durham like a few years ago. Ryan is of course an expert on supermassive black holes and AGN, and he's really stayed in the Northeast as far as I can tell. You're in Rhode Island,
right.
Yale, Harvard. Then he went really northeast and went to Durham, and then he decided to come back, and now he's at Dartmouth. Anyway, so he's here all day, and hopefully you'll have a chance to talk with him. He's a super nice guy, super engaging, and I'm really glad that he's here. So, thank you, Ryan.
Thanks, Dean. And thanks very much for all of you for coming. And yeah, as she said, I've been hoping to come here over the last couple of years, and there kept being certain things cropping up in the way, so I appreciate the flexibility in being able to make this work, and it's really great to be here. I've heard about this department a lot, and I just, this space is really makes me feel very invigorated. So today I'll talk about hidden monsters, new windows on the cosmic evolution of supermassive black holes. Specifically, what I'll discuss is what new things that we're learning about the evolution of supermassive, or sorry, obscured growing black holes, or obscured AGN. And what I'll do is highlight a lot of work from people in my group at Dartmouth College. So this is a big field, a lot of different people are working in it, but mostly today I'll describe some of the work that students and postdocs in my group are doing. This is just a overview of the groups of people that are in the group now and also have worked with us in the past. This is a picture of Dartmouth. It's very nice. It doesn't look like that today at all. It's 20 degrees and blowing wind this morning, so it's actually nice. I got here and got up for a run, went out for a run this morning, and I felt like, yeah, I could do that. Okay, so in terms of the outline, I'll give a very brief introduction to AGN and obscuration. They're mostly astronomy experts here, so I'll make this pretty quick. And then the bulk of the talk, I'll describe the work that my group is doing in trying to understand the evolution of powerful obscured quasars, which are a relatively poorly studied population of growing black holes that we think are really important in understanding galaxy and black hole coevolution. And then finally, at the end, I'll give a very brief preview to the work that we can do studying obscured AGN at high redshift with the LINX X-ray mission concept that's being studied by NASA at the moment and that I'm involved in. Okay, so to start, let's just sort of zoom out to the big picture. Has anybody seen this Sloan fly-through before? If you haven't seen it, so this is a 3D representation of the Sloan Digital Sky Survey, where they're actually showing the sort of a fly-through of the local universe. So these are real images of galaxies showing their spatial distribution and also all the different properties of the galaxies we have. I love this. I also love it when you show this to undergraduates, you have to make the point that this is not a realistic view of flying through the universe. You can't go that fast. You're flying way faster than the speed of light here. And by the time you got from one side to the other, the universe sort of changed a little bit. But anyway, so I show this to. Is there any way to turn off the lights really quick? Actually, just to. Okay, cool. I don't have any other dark movies with this. There we go, that's better. Here we go. So the reason I show this, I often show this at the beginning of the talk, is just to lay the big picture question of what we're trying to do, correct? We're trying to understand, we have this population of galaxies and this large scale structure in the universe around it. Why does it look this way? It's sort of like, looking at a whole population of animals on Earth and trying to ask questions about evolution. How do they actually come to be that way? It's the same kind of fundamental question. Why does the universe look the way that it does around us? And in order to do that, we have to understand the evolution of galaxies, which of course many of you in this room are dedicated to studying.
Can I ask, sorry, since you're starting to play the details, is that just the ones with spectroscopic redshifts?
That's a good question. I really don't know. Actually, I think it must be.
I think it must be.
Because I don't know what other.
It's like a factor of 10 more populated. Or
they probably have done some. Yeah, I don't know. I'm not sure exactly how this was put together.
Yeah.
That's a good question.
So as we're flying through, are we also going back in time?
No, not in this picture. So this is just the local universe,
So
and
this
this is
is local,
just the
okay.
fly through of the three-dimensional distribution.
What, out to a redshift is like 0.01 or 0.1?
Yeah, this is really, really low redshift. That's beautiful. Right. We can turn the lights up now. So that's all. Actually,
Oh, the button's on the right. Just start pushing it until something happens. Go for number 2 or number 3. Not that one.
definitely can't see that one.
Sorry.
It's okay, no worries. We have the exact same confusing system in our auditorium at Dartmouth.
So they just do that.
I'll get rid of those. Everybody's got to chillax.
Doesn't matter, or whatever.
Somebody let me
Conference was here
No.
2 weeks ago, and then they started doing this.
Cool.
What's this, disco mode?
So specifically, what I'm interested in studying, what our group is interested in studying, is a particular kind of galaxy. So here's galaxy. It's sort of typical spiral galaxy, and most galaxies look something like this, as you saw in that video. But every once in a while, if you look at a galaxy, instead it looks like that. There's a very bright point source in the center, and that, of course, is a quasar. And so our group is understanding sort of trying to understand what are these kind of objects, what are the things that produce them, etc. But one of the things I think it's important to take away, again, sort of as big picture motivation, is just to remind yourself actually what a quasar is and how powerful it is. So the total amount of power in a quasar is 10 to the 47, and a powerful quasar is 10 to the 47 ergs per second. And you can throw these numbers around. Okay, this is a really big number. What does that actually mean intuitively, right? Like, how do we have any idea how much power that is? And so I like to do a little experiment where you say, okay, let's think of something of which there's a really big explosion and you can have lots of them. And exactly how many would you have to have? So can anybody think of what's the largest man-made explosion that humans have ever produced?
The solder bomba was exploded at the end of October 1962. The yield was between 50 and 58 megatons of nitrogen.
Right. So it's a little, I don't think it's quite that much. I didn't use that one. I think I used a normal, one of the lower yield hydrogen bombs. But a hydrogen bomb produces about 10 to the 24 ergs of energy if you convert from megatons to ergs. Now, what's something of which there are many on the surface of the Earth? It's the example people always use. On the beach.
Grains of sand.
Grains of sand. So how many grains of sand on the Earth? Nobody would have any intuitive idea, but people have estimated this is about 10 to the 22 grains of sand on the surface of the Earth. So if we multiply these two numbers together and compare it to this number, you can ask how many hydrogen bombs would you have to have go off per second per grain of sand on the surface of the Earth to produce a luminous quasar? And the answer is about 10. So if you think of that for a second, I love that because it gives you kind of like an intuitive view all of a sudden of how much power is being produced by a luminous quasar. It's an absolutely ridiculous amount of energy. But that's, these are the things that we are studying. So what produces this? Well, of course, go.
Let me just make a comment. So if global warming is going to raise the ocean level, will the number of sand go down? Somebody was calculated that.
That's a great question. I don't know whether this counts sand underneath the ocean or not. Yeah. Probably only in order, less than an order of magnitude. Anyway, so what produces this? Of course, it's a supermassive black hole. And so that leads us to kind of the big picture question that our group is asking when we're studying these quasars. What we're really asking is, what is the origin of these supermassive black holes and galaxies? We know that now most massive galaxies have supermassive black holes in them, and we know that they gained their mass through this process of accretion. And so what we want to do is trace the growth of these growing black holes as they grow as active galactic nuclei. And that's one of the main research goals that our group is trying to accomplish. So everybody's seen a picture like this, but just to give a quick background. So what is an AGN? Well, you have a black hole in the center, you have an accretion disk of material going onto this black hole, and the main thing to take away from this is that the luminosity of a black hole can be written down that the sort of accretion process is relatively generic and extremely efficient. So if you write down what's the luminosity of a black hole, you can write down the change in rest mass energy times some efficiency factor. And that efficiency factor is really high. It's like 10%. Whereas compared for fusion and for PV chain and stars, it's only about 0.7%. So this is one of the most effective ways of liberating energy in the universe, turning mass into energy. And the key point is that if you measure L, if you assume something about epsilon, then you get end up. So by looking at active galactic nuclei, growing black holes, you're actually tracing the growth of the black holes and their galaxies over the history of the universe. Now, an AGN is more complicated than this. This is a more recent schematic picture of what's going on in a black hole, and you have an accretion disk, or sorry, a supermassive black hole. This is now log of scale, so you can see that the structures in a black hole go over many orders of magnitude. You have an accretion disk, you have a broad line, where you have a hot corona that produces X-rays, you have a broad line region of fast-moving gas right around the black hole, and then you have a narrow line region of slower moving gas, and you have some dust that's distributed around the black hole as well. And due to all these different emission components, these then actually produce a very broad spectral energy distribution for the emission that comes from a black hole. So your accretion disk has temperatures of tens of thousands of degrees, so it will peak in the UV part of the spectrum. The dusty torus around the black hole will peak in the mid-infrared part of the spectrum. The corona is really hot. It produces X-rays through inverse Compton scattering, and then also if you have a relativistic outflow, you can produce radio as well. And so if we look at the spectrum of a black hole over a wide range of wavelength or frequency, we see all these different components that produce a very, very broad SED. And it's this studying of the SED that we use to actually understand what's going on with these systems, and I'll show a bunch of examples of SEDs like this as we go along. Okay, so just to make the point, again, L is proportional to m dot, approximately, so we can actually use AGN to trace the black hole growth history of the universe out to very high redshift. So this is redshift now, and this is both the star formation rate and determined from various star formation rate indicators, and the density of star formation, and then also the space density of black hole accretion from measurements of the AGN luminosity function that you can then integrate to determine the black hole accretion rate. And they broadly trace each other with a peak between redshift 1 and 2, suggesting that there's some global connection between the growth of structures in the form of galaxies and the growth of black holes in the form of accretion. But what we really want to do is actually go measure how many growing black holes there are out there and trace this over cosmic time. Now the thing that makes this hard, so this sounds relatively easy, right? You have this black hole, just go forward. You have this black hole that's producing radiation across the whole electromagnetic spectrum. So you just go measure some of this radiation that's coming from the growing black hole. You do this for many different redshifts, and you piece together the overall accretion history. The thing that makes this hard is that most growing black holes actually don't have an SED that looks like the one that I just showed you, because they are hidden behind a shroud of gas and dust. So this is the first ever discovered quasar, 3C273. This is one where you have a very clear picture down at the accretion disk. The thing is booming bright at every single wavelength that you could look at. This, however, is a high redshift, very rapidly growing black hole that looks, for all the world, in its optical image, just like a regular old galaxy. And that's because there's material blocking your view to the accretion disk that takes most of those emission components and absorbs them, so you can't see them anymore. And so identifying these hidden black holes is a major challenge that we've only really had the observational capabilities of doing in the last, say, decade or 15 years. Another important piece for those who are interested in it is that these obscure growing black holes actually produce the bulk of the cosmic X-ray background. So the cosmic X-ray background was the first ever background discovered. It was actually discovered before the cosmic microwave background. And it's now known to be due to the sum of emission from many, many growing black holes. But if you look at the spectrum of the whole cosmic X-ray background and compare it to the spectrum of a typical AGN, like I showed you before, in the X-rays, they don't match. And what you need is a population of highly obscured black holes to actually account for all the X-rays that you see in the universe. And so this is another hint that tracing this black hole accretion, you actually need to understand these obscured objects to know what's going on. Okay, so again, just to summarize that piece, we need to understand, why are we doing this? We need to understand obscured AGN to obtain a complete census of the black hole growth in the universe. Most of it, as you'll see, is obscured. To determine the accretion physics, such as the global radiative efficiency, as we'll see a little bit later on, and also to understand the origin of the cosmic X-ray background. And finally, and this is in a lot of ways maybe the most exciting thing, is to understand the mechanisms of black hole fueling and black hole galaxy coevolution. Turns out some of the most important phases of black hole growth are probably these obscure things, and so we need to be able to find them and characterize them to understand what's going on. So this is a fun topic. This is one a couple of years ago we actually had a whole conference at Dartmouth about this, called the Hidden Monsters, so that's where the name of this talk comes from. Dave Alexander, my colleague, co-organizer here, who I worked with in Durham, and I, are now also writing an annual reviews article that's just in press now, so you can look out for that pretty soon. If anybody would like a copy of it, I can send you the sort of advanced copy, but this sort of covers a lot of the topics that we'll discuss in the talk. Okay. So how do we define what an obscured AGN is? Well, we have this sort of structure of a growing black hole that has, again, this accretion disk within this sort of dusty torus around it. And an unobscured object is typically one where you can observe all the way down to the accretion disk and the hot corona, and so you see the full SED that I showed you before. For an obscured object, there are many different types of structures that could produce obscuration. One is if you're looking just along the wrong direction through this, towards this black hole. If this torus structure is tilted along your line of sight, then you won't be able to see the accretion disk and the hot corona. Or if you have actually, say, a merger of galaxies or some other galactic scale process, you could actually then block the light towards the center that way as well. And typically, we define an obscured AGN as one where the characteristic kind of definitions we use are one where the obscuration is greater than 10 to the 22 centimeters per square centimeter, or the extinction is larger than about 3. In either case, you will block the light enough that your traditional diagnostics don't work. And so we're trying to identify objects using this way. As a point of comparison, an answer 10 to the 24, I'll use this in a few things as I go along, is Compton thick, meaning that the optical depth, the Compton scattering is 1. And so it turns out your hand is about Compton thick. So X-rays, hard X-rays can pretty much pass through your hand. If you put many, many hands next to each other, then the X-rays wouldn't be able to pass through them, which is why we use them for X-rays, right? Bone basically blocks it and tissue doesn't. And so it's kind of crazy to think that a heavily obscured AGN actually only has, as we'll get to in a minute, only has as much column density of material as your hand. So if you go to stand in front of a black hole and go like this, you would block you with some distant observer. You'd get fried. Yeah, and you would not be nearly big enough, but the point being that, this is the kind of columns that we're talking about.
Covering fraction's still low.
Yeah.
That's right. Covering, yeah, it's a patchy absorber. Yeah. Okay. So now we're getting into the meat of things here. So how do we actually identify these objects? I mentioned that the sort of traditional SED gets absorbed. What am I talking about? So here's a little movie that we made for our annual reviews article that shows some images of a galaxy at different wavelengths. And then this is the spectral energy distribution of the galaxy and also the hot gas and X-ray binaries in the galaxy. And what I'm going to do is ramp up the luminosity of the AGN, and you'll see the images change, and you'll also see the SED change. And then I'm going to add in some obscuration, and you'll see what happens. So first, if we ramp up the AGN, we get to the point where the AGN begins to dominate these images, and you can see then the thing basically becomes a point in all of these different images. And then when you produce obscuration, it preferentially absorbs certain parts of the spectrum. In particular, it preferentially absorbs the ultraviolet and optical, that's the dust absorbing that, and then the gas will preferentially absorb the soft X-rays. And so many of your signatures, your sort of blue accretion disk, your large soft X-ray luminosity, your broad emission lines, those are all gone when you have the obscuration. But you can still see other signatures like the emission from the dusty torus and the hard X-rays and the high excitation emission lines. They're still all there. And so these are the mechanisms that we use to identify these objects. So just to go through a few of these, so this is in the optical, what you do when you're seeing an obscured AGN is you basically see something that doesn't have broad emission lines due to the stuff right close to the black hole that's moving fast is gone. So all you see is narrow emission lines, and you don't see the blue continuum from the accretion disk. So here's a spectrum of what are called type 1 and type 2 AGN. that have these two separate emission characteristics. In the X-rays, what you see is the soft X-rays getting absorbed, and all you see is this Compton hump out to hard energy. So this is a heavily obscured AGN identified with XMM and new star. So there are these characteristic features that you see when you're absorbing away the low energy X-rays. In the infrared, what you see is that if you were to look in the infrared, you can see this is now a rest wavelength going this direction. For an unobscured AGN, you see light again across the whole. This is flipped, by the way. This is wavelength instead of frequency, like the ones I showed before. But you have you can see the infrared part from the torus, and you can see the ultraviolet part coming from the accretion disk. For an obscured object, in the ultraviolet, you only have emission coming from the galaxy, but you still can see emission from the AGN in the mid-infrared. And so this is, in a lot of ways, the most effective way of identifying these heavily obscured AGN is looking for these infrared signatures. And here's just a sort of comparison of different AGN selection techniques that show the various obscuration and dominance regimes that we can try to identify these objects for. I'll skip past this, but you can find this in the article if you'd like. Just to make the point that you got to use many different techniques in order to piece together the whole obscured AGN population. Okay, so we have all these techniques we can use to identify these things now. What's the physical nature, though? What actually is doing the obscuring? Is it this torus that's very small, say 10 parsecs in size, or is it something on the scale of the galaxy that can be kiloparsecs or up to 10 kiloparsecs? What's going on with these different structures? Well, so we start with the torus. The torus is this material that's going around the black hole and probably connected to the inflow and also some of the outflow and radiation from the black hole. People always draw it as kind of simple static donut like this, but if you actually were to do a simulation of it, instead it looks like a much more dynamic thing. This is from a paper by Ichiwada et al. Showing the outflow from the radiation from the growing black hole, and then this sort of dynamic complex inflow. But this is, say, of the order of a few parsecs in size, so you have this high covering factor, dusty material that's around the black hole.
Is that to scale?
What's that?
I mean, that doesn't write to scale. That's sort of the picture of the torus is a much narrower.
Yes, well, I mean, the thing is, there's a very large dynamic range of density here.
Oh, okay.
So I think what you traditionally call the torus is this thing.
Got it. I see.
Right, sort of 10 parsecs, but these suggesting that
Where you
bound-
mentioned the opening angle, this will be in the green part.
Yeah, exactly. So this would suggest that you have sort of a range of columns depending on what exact angle you look at, which there actually is pretty good evidence that that's what's going on. Oh dear. Now, what's going on large scales? Well, there are simulations of this too. This is a nice image from a simulation by Laura Blecka that shows the two galaxies merging together. Here's the AGN luminosity as a function of these different merger stages, and then here's the NH, the obscuring column. As you can see, you're kind of looking through the disk the whole time here, but when you get to the near the end, where you actually have the coalescence between these objects, you have a huge spike in the column density due to the fact that the gas is collected down near the center, and you're actually looking through a large amount of material. And so this. So it's possible to, even on relatively large-scale emission, to get quite large column densities through this merger process as well. And one of the things that we point out in our review article is that the level of obscuration you can get really depends on the scale. If you look at a very large host, or you look on the scale of the whole host galaxy, it's impossible to get really large columns because otherwise the massive gas that would be required to sustain that would be way too big. So if you assume a constant mass of gas, that's just going to be the R cubed, the volume of the object, times the column density. Or sorry, times the volume, the space density. And if you write that in terms of column density, then it's R squared times the column density. So for a given mass of gas, the NH just goes as the mass of gas divided by the square of the radius. That, of course, you will get bigger gas masses as you go farther out. But this is just making the point that you can't get an enormous column on the whole scale of a huge galaxy unless you're looking on one very specific line of sight, because otherwise you have way too much gas. So the highest columns happen down in close, near this nuclear torus, which is only on scales of, say, 10 parsecs or so. Okay, so when we actually go and observe a bunch of obscured AGN, one of the most obvious things you can measure is the distribution of obscurations. Go find them and ask, what is the, how many AGN do we find at these different obscuration levels? Remember, 10 to the 22 is our sort of classical cut between unobscured and obscured AGN, and 10 to the 24 is our Compton thick limit. And if you observe, see what we observe, you find this red line here. If you actually then correct for various selection effects, you find that it gets tilted way out to higher column densities. And so if we then map this onto the previous slide, you know, these smaller amounts of obscuration could presumably be due to the host galaxy. You can have sort of medium scale nuclear starbursts producing up to say 10 to the 24, and then your torus will potentially give you even higher columns. And so we're probably not probing just one process, we're probably probing many when we look at this whole distribution of obscured AGN. The last point to make, which I think an important one, is that if you do this kind of estimation as a function of luminosity, you can calculate what fraction of the AGN that we see are obscured as a function of luminosity. And so this was a nice paper by Sylvia Mateos from last year that shows the observed AGN obscured fraction, which decreases at higher and higher AGN luminosities from, say, 60% are obscured down to 20%. But if you correct for selection effects, remember obscured AGN are harder to find because they're fainter. If you correct for selection effects, you end up getting a distribution that's about flat. And so the key point is that at all luminosities, most black hole growth, something like 60%, is obscured. It's not identifiable in traditional, say, optical surveys. And this is true even up to the highest luminosities. So this now gets us to describing, there's a lot of background, but this now gets us to the meat of the talk, which is what our team at Dartmouth is doing. It's only recently been recognized that most of even powerful AGN in the universe are obscured, and that population is relatively poorly understood. And so our team is really trying to understand these very luminous AGN, what's going on with their physical properties. So I'll go through three quick things that we're doing. One is how can we identify obscured quasars? Second is how heavily buried are they? And finally, four, what outflows do we observe from them? And then lastly, what are their host galaxies and large scale structures? And I'll go through each of these in a few minutes. And again, this is the whole wonderful team of people who are involved in all this work. So the first question, how can we identify these things? Well, as I mentioned before, some of the best indicators are using the mid-infrared. And AGN looks very different from a galaxy in the mid-infrared. And the mid-infrared is not very well affected by obscuration. So if you can look in the mid-infrared, you can find a lot of powerful quasars that are otherwise not identifiable. And so our group's done a lot of work using color selection techniques. I mean, Casey's been involved in a lot of this stuff over the years too. I won't go through the details of this plot, but if anybody's ever seen, say, mid-infrared color plots, this will look familiar. Basically, AGN are a lot redder than galaxies for the most part, especially in this particular wavelength range in here. And so if you plot color versus color, your quasars show up in the red part of the spectrum, a larger color up here. And so we use a color cut like this to identify a large population of obscured quasars and try to characterize them. Now, one of the things that's not clear is if you just use a simple photometric cut, where you did purely based on mid-infrared observations, how often do you pick up things that really are quasars? And in particular, we're looking for things that are like quasars, that are faint in the optical and extended in the optical, because they look like galaxies in the optical, but they have the colors of quasars in the mid-infrared. Well, the question is, how often are these things really quasars, and what if there's some kind of weird star-forming galaxy or something like that? So our group has done a lot of work on this. What we've done is done a blind search for obscured quasars using data from WISE, the Wide Area Infrared Survey, Sloan Digital Sky Survey. They give us the optical, and then we've gone and followed these up with spectroscopic observations, particularly with SALT, the Southern African Large Telescope that Dartmouth has a lot of time on in South Africa. So we did this, and what you find basically, so here's some SEDs of these objects. We get redshifts for them, and this is work that Kevin Hainline, who's now at Arizona, Chris Carroll, who's a grad student of mine at Raphael Vinning, who's actually graduating senior, he's doing this for part of his senior thesis, his paper just got published. We got redshift for these things and also got optical line diagnostics. And it turns out if you do optical line diagnostics, pretty much all of them have high excitation emission lines that tell you that there is a hard underlying nuclear source in there. This thing really is a quasar. And their SEDs give us some estimates, for example, of how heavily reddened they are. And so the key takeaway is that this simple color selection, photometric selection technique that we use to find obscured quasars is effective. It does work. And recently, we've had a lot of success with this. The original work that I did on this, I actually did some work like this for my thesis. Were you on that paper? You might. This was some booties. Yeah, I think you might have been.
Yeah, very possible. Yes,
I seem to recall a lot of discussions. Yeah. So this stuff I did for my thesis. At the time, we found a population of 600 obscured quasars in the Booties 9 square degree survey field using data from Spitzer. This was an enormous number. Previously, there was one optical selected sample that had a few hundred, and otherwise the largest samples were in the orders of tens. And we went and found, in the survey, we found 600 obscured quasar candidates. This was like a really big deal. At least to me it was. I was a grad student, so it's like, yeah, exciting. And so we did a bunch of work with this sample. But then, when I was a postdoc, we saw the release of the WISE data set, which doesn't just cover one little 3 square degree by, or 3 degree by 3 degree patch of sky, it covers the entire sky. And if you have also optical data, like with Sloan, you can now identify the obscured quasars using this gigantic sky coverage. So you go from having a few hundred of them to a few 100,000 of them. This is actually just one patch of Sloan. And so this is work that's been led by my postdoc at Dartmouth, Mike Pompeo, doing a large statistical analysis. This is the corresponding size of the field. So you can see there's just a huge increase in statistical power. And now he's actually been able to spread this over even more sources. So Mike has really led the way and is really the expert on the statistical studies of these obscured quasars using this WISE data set. So this is amazing. Now we have statistics where we can actually start to work with these things. And I'll show you some of the fun stuff that we've done with that in a little bit. Okay, so now that we have them all, one of the questions we want to ask, the next question is, how heavily buried are they? I showed you before that NH distribution tells us something interesting about the physical properties of what's going on with the obscuration. And so we want to know, what actually is the column density towards these things. As I mentioned before, if you put in a lot of obscuration, the infrared is relatively insensitive to it. So the infrared by itself is not a really good measure of the obscuration. But as you'll notice, the soft X-rays and even the hard X-rays actually start to be absorbed pretty easily once you get up to high column densities. And so the ratio of the X-ray to the infrared emission gives you a really nice clean handle on the level of obscuration. Here's just one example of a heavily buried quasar that we've just found using data from NuStar. This is Alberto Massini, a postdoc in our group, again showing one of these SEDs, and you can see evidence for exactly the kind of absorption that I was showing in that schematic. So how do we do this? Well, again, the way we do it, this is work by George Lansbury, who's now at Cambridge, actually, who's done a bunch of stuff on this. You take the infrared luminosity of the source, you look at its X-ray luminosity. You know that if it's not obscured, there's actually a really tight relationship between how bright an AGN is in the mid-infrared and how bright it is in the X-rays. And you can sort of write down that relationship. But if you have obscuration, what it'll do is not really affect the infrared, but it'll strongly affect the X-rays, and so it'll bring down this observed X-ray luminosity. And this offset you can use to measure the obscuration. And so again, we have, remember this is what was seen for local. This is actually the SWIFT-BAT AGN sample, a very low redshift that was seen by Claudio Ricci. And George has done the same kind of thing now for quasars at higher redshift. And he found that when you correct for all the observational biases, particularly using the hard X-ray information from NuStar, that you get a similar kind of distribution where you tend to be dominated by very heavily obscured AGN. However, you'll notice that even in George's work, there are no sources with confirmed column densities above 10 to the 25. And the reason for this is kind of obvious. That produces so much obscuration that you won't expect even to see detections in the hard X-rays. But the question is, are there some of them out there? Are there these really, really heavily buried AGN? And so we tried to answer this question. We went and looked at some of our Y-selected quasars that we observed with SALT. We also observed them with Keck. And again, confirmed that they were luminous obscured quasars. Here's an example of one object. Here's its very heavily reddened AGN SED, and then here's the spectrum. This is work that's being led by my grad student, Vivian, who has, this paper is now submitted. And so she went and observed this with NuSTAR, the hard X-ray observatory that observes out in that high energy range that I showed you before. Of the 4 objects we observed, 3 of them were completely undetected. Gone, not in the NuSTAR survey at all. You don't see anything. It was getting to the point where I was actually afraid we had pointed at the wrong target. Like we started getting these data in, and there was nothing in the images. And then we finally got one, and oh look, there is, if you squint, you can maybe see a little smudge there. There's a detection. So if you put them on the plot that I showed you before, this is just another version of that same infrared versus X-ray plot. All these things are way down below the relation you would expect for unobscured sources. And so the NH is well more than 10 to the 25. So there's this new population. We've uncovered this new population of very heavily obscured AGN that were not necessarily known before, and it skews this NH distribution even farther over. Which A, tells us that there's just a very heavily buried population that you would never see at all in an X-ray survey, and also tells us something about the potentially, for example, the structure of the obscuring torus. This kind of really heavy obscuration has to be happening close in, but these objects had not been seen before. Okay, so that's how heavily buried they are. The next question is, what is going on with our host galaxies and large-scale structures? So those of you here are interested in galaxy evolution, this is kind of getting into the meat of what the black holes do. And there's a very simple test you can do to try to understand, by studying their host galaxies and large-scale structures, you can do to try to understand the nature of the obscuration. If you have just a torus, where the only difference between the obscured and unobscured things is the orientation, then there should be no difference in the large-scale properties, because it's just whether it's turned towards you or not. However, if there are galaxy scale interactions, then or structures or interactions, then you might see such a difference. And so we've gone to try to study this in a number of different ways. So this is a piece of work by my grad student Chen-Ting Chen, who did this for his thesis. He's now a postdoc at Penn State. And so he studied obscured quasars and unobscured quasars, and in particular looked at the far infrared, which is an estimate of how strongly star-forming they are. And what he found was that if you look at higher and higher star formation rates, the fraction of quasars that are obscured goes up significantly. So this tells you there's a link between the obscuration of the nucleus and what's going on in the star formation on larger scales in the galaxy. Because otherwise, if it were just orientation, these two things would not be connected. So that's one piece of evidence. Another bit of evidence that a lot of different people have looked at is that obscured AGN are commonly found in mergers. If you actually look at the morphologies of them, if you go to higher and higher columns, you tend to find a larger fraction of objects that are in galaxy mergers. And so this is work done by Alok Glickman and Middlebury, Dale Kachevsky and Colby, and a number of others.
It's still somewhat controversial, though. I mean,
What's that?
depending on how they do the comparison samples, like even Dale has come up with different answers.
That's true. So this is more, you're right, this is more controversial than I would think. Yeah. I think actually the interesting thing with Dale's one is that the data, I mentioned that you get a higher obscured fraction as you go to higher columns.
Yeah.
What we see now in the data we've been looking at is actually not out here, it actually peaks and comes back down again. Which is what you expect based on the distributions of the columns in the different scales that I showed you before, right? You wouldn't, it's kind of crazy to say that a 10 to the 25 column would necessarily be associated with a merger, except in a very, very small window, as shown in Laura Bleck's simulation, because that would just require too much gas.
Right.
But 10 to the 20, between 10 to the 22 and 10 to the 23, you can totally do in a garden variety merger. And at least some of the work that Mike Pompeo is working on now looks like that's actually what's going on.
That kind of makes sense. I mean, they're saying, like, for the really obscure things, you need a lot of gas, not just a lot of gas, but compressed.
That's right.
A small space around the
Yeah.
black hole.
So it should be a relatively short-lived phase. But,
But there are galaxies this type that have CO columns that would be consistent with 10 to the 24, right, or 10 to the 25.
Is that right?
Depends on the X factor you use, but yeah.
Okay.
They get, it's like 10 to the 3 or 10 to the 4 solar masses per square parsec, which is sort of near the limit.
Right, yeah.
Yeah, this has got to be like the major universe, right? Or,
Yeah.
right.
Yeah.
So you do have to get a lot of gas compressed.
Those quasars, a lot of these quasars are very bright CO sources.
Yeah, so then you could ask, well, then why do you see some of them that are totally unobscured too, right? You actually do see some systems where they're pretty unobscured, but they still have a pretty high CO mass. So that tells you that the distribution has to be anisotropic, and you have, so it's I think this particular question is really complicated. And sort of, yeah, you're right. I
That's good.
glossed over a lot of.
It's obviously interesting, right?
Yeah. So the last thing, the thing our group is really focused on a lot are large-scale structures, where we try to ask what are the kind of halos, in particular dark matter halos that these things live in. And the way you study that is by studying the two-point correlation function, which AGN clustering is one of those things like, sort of like weak lensing, or it's sort of like other stuff where if you don't, people who haven't done, or sorry, the galaxy clustering in general, people who don't do it sort of, it seems like a black box, and people who don't do it often think, I don't know what you're talking about. X-ray data analysis is kind of the same way. I guess sort of like interferometry. Things where if you don't do it, often people think, I don't really know what's going on, but I'm just going to trust the result that comes out of this. It's particularly true of graduate students who will eventually learn these things. But I just want to give you a really quick primer. The two-point correlation function is actually really simple. All you're asking is, what is the probability that you will find 2 points in a distribution that are at some distance apart from each other, above what you would expect if they were randomly distributed? So here's a relatively random distribution of objects on the sky. This is a 2D correlation function, and they're very weakly correlated. Now, if I make a stronger correlated one that looks more like a galaxy distribution, you see that they're more likely to be close to each other on small scales, and it falls off on larger scales. This is the way that hierarchical clustering in the universe produces clustering, and so this is what you see when you look at galaxies. So we know, based on simulation, this is now an old simulation, but it makes the point, if you go up in that dark matter halos cluster in a very straightforward way. If you go to higher halo masses, you get stronger clustering in this two-point correlation function. So if you can measure the correlation function, you can back out the masses of the systems that are residing in them. So it's really clever. You can't see the dark matter necessarily, but if you measure the way they're clustered, it gives you some handle on what kind of dark matter halos they're residing in. And so we've done this. We started doing this with that old Spitzer sample that I told you about. So this is the first project I did as a postdoc. We found them when I was a grad student, and we measured the clustering when I was a postdoc. And what we found, so we looked at the clustering of obscured, this is in red, and unobscured quasars. And what we found was that, well, okay, so this is now a question for the grad students. Is that significant? I expect to see some head shaking. I hope so. That's not significant, right? But there was a potential issue with the photometric redshifts in the survey that would have at least decreased the clustering signal of the obscured things and not decreased it for the unobscured things. It's a technical detail. So what I said in this paper when we published this was that, and by the way, so this is redshift and this is the halo mass. So this is telling you that the unobscured quasars are found in halos around between 10 to the 12 and 10 to the 13 solar masses. That's like local group scale. You know, a small group. And that's where most of the action seems to happen in the universe. Our obscured quasars are happening they're seeming to be found in larger halos, but with a big error bar. So what I said in the paper was, we've shown, and I got so much flack for this, because people said I was claiming that there was a difference, and I was not. What I said was that there is at least as large a clustering for these objects as those, which I think you can make a significant claim in that direction. Anyway, so
your statement about the bias, I'm actually curious. So is it pretty much just saying that the photometric uncertainty on the obscured ones is going to be broader, it's just going to wash out the signal out and try to invert the 2D cluster to 3D?
Yeah, that's right.
And that would be stronger, more of a bias in the obscured population. You get by that.
So it would bring these up, right? Although we
That
did a lot of
bias would actually move, right, would move those up.
right,
Yeah.
but we did a lot of tests of it, and we showed that effect is probably not that large. There's a whole technical thing involved with this that we don't have time to get into. But anyway, I have another question to the grad students. When you have a signal like this, it's barely significant. What is it that you need?
More data.
Oh, come on, more data. Yeah, as you've seen, the end of every single observational paper ever written is we need more data, right? So we need more data. Well, thankfully, we have more data now. We have this WISE survey that I told you about before. And so this is work that Mike Pompeo did. He now just did an angular clustering since we didn't have spectroscopic redshifts for everything. But lo and behold, he found that there was a result that was, again, consistent with some difference. Okay, so we're starting to believe this. But we also wanted to have some independent check of whether or not this is real. And it turns out that a few years ago, a great opportunity came to us in that there started to be maps of the lensing of the cosmic microwave background due to large-scale structure. So this is cool. You can take the CMB. If you put large-scale structure in front of it, this is really highly exaggerated. But what it will tend to do is take the structures in the CMB and lens them. And you can back out the, from an analysis of the CMB signal, you can back out the actual integrated lensing signal in different parts of the sky. So this is the lensing map that was made by the Planck collaboration from their CMB maps. So what you can do then is cross-correlate the positions of quasars with this lensing map, and that will give you an independent measure of what is the halo mass that they live in, because it's telling you how much dark matter is along every line of sight. So here's a great, one of the first papers on this. First paper was by Sherwin et al. The first one about with infrared selected quasars with done by Jim Geach and our collaborators. And I like this plot because it shows this is in the stacked image of quasar density and the positions of these different quasars. So this is low density and high density. And then this is the lensing convergence at each one of those. You can see beautifully correlated. Where there are not very many quasars, there's low lensing. Where there's a lot of quasars, there's high lensing. And if you then do this more accurately with the whole Planck maps and find the power spectrum, which Mike Pompeo has done, then you get these particular signals. And once again, you see that the obscured quasars are more strongly clustered. So this is well as much of the sky as we could probe with our Sloan sample, like a quarter of it. Yeah.
The quasars don't make a foreground signal in the CMB that would mess up the rest.
So that's a really good question. I don't think so, because I think they get smeared out. And we tried it with, so we tried it by eliminating the radio for loud things, which are the ones that you really would think could make the foreground didn't make any difference. But yeah, no, that's a really good question.
I'm going to ask one question about this.
Yeah, sure.
Maybe do it.
I think we have, I'm almost done.
Okay, I'll come back to that.
Oh, wait, yeah. So now, we started with these data points, and slowly over the years, we've beaten this down, and now, if you do a proper statistical average, we have these data points. So there really is some difference in the clustering between these two sets of objects, meaning there's a difference in their halo masses. This is not what you expect. And so now we've been trying to figure out why, what's going on here. And in our papers, we, for a long time, put this sort of straw man argument. I think it came out of a conversation that I had with Phil Hopkins at one point, where we were throwing out ideas, and we thought, okay, here's one idea that could work. What if you have the quasars are fueled in some kind of, dramatic event like a merger, where the black hole grows really fast? Then what will tend to happen is that as the merger happens, let's imagine that the black hole is obscured in the early stages and then unobscured in the later stages, which is what you expect from some of these models of black hole feedback. Then what will happen is the black hole will grow really fast in the obscured phase, and at that time it will be undermassive relative to its halo. So for a given luminosity, our actual samples are luminosity limited. For a given luminosity, you will be then in a larger mass halo than you would be for the thing once it reaches its final mass. So I think it was in like 2 or 3 different papers, we actually wrote down that this was one possible explanation. But at one point, Mike and I were sitting around and we said, okay, we've been saying this for a couple of years. Like, does this make any sense at all? Will this actually work?
Sorry, right. Could you repeat that argument? So it actually sounded like you went the wrong way. You're saying that when it's in the deeply obscured phase, it would be undermassive relative to its halo.
Right.
It's
So,
opposite to what you see.
but then you make a luminosity cut. This is the key thing. Then you make your luminosity cut, so that pushes your obscured things up.
Okay.
Right.
Got it. So that's a luminosity.
Yeah, that's right. And so Mike made a model to do this. And so here's our simple model. We have, oops, these labels got messed up. But anyway, we have some black hole, some halo that's growing over time, and it has some stellar mass that's growing over time. And so then there's some mass that you expect a black hole to have if it was just on a simple black hole galaxy scaling relation. And so what we did is it allowed for this episodic growth, where the black hole just grows really fast, and basically what happens is if we get too low, it goes through some process where it grows back up. This is totally, not entirely physical, but it's just to see whether this works. And what we said is in the early stages, the black hole is obscured, and in the later stages, it's unobscured, and then we also allow some flickering to make it a little bit more realistic, and see what happens. So when Mike does this, he goes through this process and does the, I don't have time to go through all the different steps, but the key point is that when you then apply your luminosity limit, you get out halo masses that actually look a lot like what we observed. Now there are some issues having to do with what the expected luminosity functions would look like, et cetera, that I don't have time to go into, but this is at least one broad explanation that maybe some evolutionary difference in the obscured and unobscured objects, or different evolutionary phases could explain some of these results. So the main thing I would take away is that many, not all, but many obscured quasars appear to represent a phase in their evolution of their host galaxies. Leave it at that. Okay, then the last thing to mention is what outflows do we observe from these things. In those models, you also expect that AGN should be producing some radiation that produces a lot of feedback. And so Mike has done some nice work looking at the O3 line profiles of obscured and unobscured AGN. And what you find is that you have these broad blue wings to the O3 line profiles. And he did an interesting study where he looked at, okay, what if I take the reddening of the AGN, how does the strength of that blue wing depend on the AGN reddening? And it turns out that this blue shift of that line actually gets peaks at sort of a middle, sort of modest reddening, and then turns back over when you get to larger amounts of reddening. Again, this, if you convert this to an NH, this sort of corresponds to, I don't know, about the distinction between obscured and unobscured. So this would be about 10 to the 22. And this is what you expect for sort of a screen of gas or, and dust around the black hole. And it's there when you're looking through that kind of column that you see the most extreme outflows. So this is consistent with some pictures that if you have, it's a high enough column, you have too much stuff hanging down in the black hole. But if you have lower columns, then you can actually drive out a large amount of gas and dust. So we can discuss this more as we go along, but I haven't run out of time. Okay, so just in the last minute, obscured AGN at high redshift. So now the real frontier is to try to study what's going on at the highest redshifts, out at, above redshift 5 or so. And now I'm getting into the bread and butter of what you guys will know a lot more about than I do. But an interesting idea is to ask, okay, how do black holes grow? How do they grow their mass in the very early universe, sort of during and after reionization? And so here are some theoretical black hole growth models. This is now the accretion rate density again at the very highest redshifts. And these are the measured points for the black hole growth observed in the very deep Chandra Deep Field South. This is work by Fabio Vito. And there's a difference. The black holes are not growing as fast as the theoretical black hole growth models would suggest. So either there's some kind of seed formation process that actually puts the black holes in place so that they don't have to grow as much between redshift 7, say, and redshift 4, or there's an early population of very obscure things that we're not picking up in the X-rays at all. And so what you need is more sensitive X-ray observations that go to even higher redshift. And so to do this, we are in the process of building a concept for a new X-ray telescope. Here's the Hubble Ultra Deep Field. This is the Chandra image, so this is the optical image showing all the galaxies. This is the deepest ever Chandra image of the center of that field, so the deepest high-resolution X-ray image. And what we're proposing is to build a telescope that instead would give you an image that looks like this. And so this is LYNX, the X-ray telescope that's one of 4 being considered for the decadal survey right now. I'm on the science and technology definition team for that. And so the idea for LYNX is that you have exquisite angular resolution that allows you to detect these high redshift sources and associate them with their host galaxies. And also if you're looking in, for example, clusters of galaxies, you can actually pick out the AGN inside the large-scale structures. So I can tell you a lot more about what we can do to this, but the idea, the sensitivity is set by being able to detect a 10 to the 5 solar mass black hole accreting at redshift 10. which would be extremely exciting if we could do that. And so again, this is what the amazing simulated images look like. I'll skip this part. So I'll leave you with my take-home messages that obscured AGN are the majority of supermassive black hole in the universe. So if you want to study them, they're really critical for understanding both the origin of black holes and their co-evolution with galaxies. These obscured quasars are really common and often very heavily buried, and they seem to represent an important phase in galaxy evolution. And Chandra and Lynx, I skipped over the Chandra one, but Chandra and Lynx will be critical for studying this later evolution. So I'll stop there. Thanks very much.
Casey, do you want some questions?
We'll go first.
We still have a few minutes. Casey, do you want to ask a question?
Yeah, we can start working backwards.
Sure.
That was all super interesting as well. I'll ask some good questions. So Lynx is super cool. I'm glad you started talking about that because I've been paying attention only because we've been working on science. I mean, the Giant Magellan Telescope. And one of the ideas is how would you identify those candidates that would want to follow up with spectroscopy. And so you're saying like the number was 10 to the 5th solar mass black holes at redshift 10?
Yeah.
Is that okay?
Yeah.
And then does that begin to rule out classes of models if you want to say like, look, you have to have this rapid growth versus the ones, I'm actually going the other way around, the rapid growth models versus the ones where you have some, we call it a seed, but you're saying like something by redshift 10 has to get you up to 100.
Yeah. You get quite different luminosity functions for those ones. But they really start to break at the highest redshifts when these things are starting to form, right? So basically, as long as if you're talking only about, say, a few times 10 to the 4th solar masses, you can get different kinds of evolution that will lead you to a similar looking luminosity function, say at redshift 6.
Okay.
But by the time you get to redshift 10, the things have either just formed, right, and so you have these black holes there, or these massive black holes there, or they're all sort of coming up really rapidly from their smaller masses, and you get significantly different luminosity functions.
It's really the shape of luminosity function.
Yeah.
I was going to ask you about the number density.
It's not just the number density, it actually is the shape of the luminosity function, and this is a key point, it's actually the conditional luminosity function. So it's the luminosity function, or however you want to call it, as a function of the properties of the host that it sits in. So you can distinguish between, one thing you can distinguish between high mass and low mass seeds, based on the different models, is that they form in different galaxy environments, right? So you would expect if you see bright X-ray source, if you see them all in very massive galaxies, if there's such a thing as a massive galaxy rich of 10, then that tells you something different than if they're all in less massive galaxies. So you really need JW and W first to give you the photometric information about the galaxies, and then combined with the X-ray information that can break these models. So we're still working on exactly, the thing is there's a lot of models.
Yeah.
So it's hard to say, I'm going to completely rule out this one
Because
scenario.
there's not much data, but there's so many models, and you just need more data to wrap that up.
Right, exactly. But the sort of straw man scenarios you can already begin to distinguish.
Does it distinguish between these obscured phases and the unobscured phases? I mean, like, would Lynx help? Would this have the? You know the numbers off the top of your head, right? I mean, can you actually begin to distinguish between the obscured AGN and the obscured ones at this?
So the obscured things. So there's two issues.
Yeah.
One is, are there things that we did not detect in Chandra that you would potentially be able to detect in Lynx? The answer is probably yes, because you'd see sort of weak X-ray signatures due to scattering or due to reflection that you wouldn't necessarily be able to see in an individual Chandra exposure.
Okay.
The other thing is when you go to really high redshift, well, you're already starting to get there by the time you're redshift 6. But the observed frame that you can, the rest frame, the observed frame that you can observe in the soft X-rays is like, say half to 8 kV. But when you get to redshift 6, and especially if you get to redshift 10, now you're probing like
The Compton bump is
way beyond the Compton bump, right? So obscuration has less of an effect out there, and in fact, you're in some ways
actually helps you.
Yeah. Now it's an issue for Chandra. I mean, Chandra already observes in the same band, right?
Yeah.
So this puts some constraints on what you can do at lower redshift. But at higher redshift, if everything was obscured beyond redshift 6, the point being that you could potentially see, all the way out to the higher redshift side.
So, just maybe this is an obvious question, but then would you, just from all this, do all galaxies go through the AGN phase?
Well, anyone with a black hole, I think, with at least a reasonably large mass black hole has to.
So everything more massive than an LMC?
That's a hard question.
Yeah.
I mean, not
thought-
necessarily,
yeah,
right? So,
I'm just trying to.
M33 doesn't have a black hole in it,
Sure,
at least, you know.
not now.
Not, well,
Or
it would
ever.
be really hard to get rid of, to kick the black hole out of there. It is a very low mass, the dynamical constraints are really strong. So not all galaxies do, and then we seem to have, Andrew and I were just talking about this, there seem also to be really massive black holes in relatively small galaxies that have undergone some other weird evolution. But it's really hard, even in the most aggressive seed models, it's really hard to make a seed that's like 10 to the 6. Or more than 10 to the 5, that's really hard. You could have a direct collapse that makes 10 to the 4, that's pretty doable. But 10 to the 5 solar masses is hard. So if anything above is, say, a few times 10 to the 5 solar masses pretty much had to have been an AGN at some point because it couldn't have gotten up to that mass any other way. I mean, it could have merged, I guess. You could have merging of seeds if you have multiple merges. That'll be a factor of review. But yeah, ultimately, I think the idea is most galaxies really were AGN at some point.
Well, let's thank Brian again.